The character Venom has a very weird symbiotic relationship when he first appears in the comics with Deadpool and then Spider-Man. But did you know that in nature, there's also other weird mutualistic and symbiotic relationships with spiders, specifically the burrowing tarantula and the spotted humming frog. These tarantulas keep these frogs almost as pets. The frogs offer protection to the spider's eggs, eating smaller pests like ants, and the spiders protect the frogs from larger predators like birds and snakes. It's a mutualistic relationship between the two of them, and sometimes you can find these frogs huddling under dozens of these giant spiders. Sometimes truth can be just as strange as fiction, or at least I like to think so. Hello and welcome to another episode of Because Science Live, the live companion show to Because Science, where I take all of your comments, questions, corrections, and weird comments about my body and hair live and try to answer them off the top of my head to the best of my ability. And when I don't know something, I will say I don't know something, because it's also good to know what you don't know. To know how vast the island of ignorance you stand upon is. To dig your toes into its sand and understand it. That's a quote by me. I have occasional voice of the void. Nate here. Nate.
Yep.
Nate.
Yep.
What we got?
From Woogie Maniac 87.
Whoa. This is gonna be a wild question.
Hi, Kyle.
Oh, hello.
Wouldn't Ironman have turned into human goo in his suit when he boosted out of the atmosphere in Infinity War?
When he boosted out of the atmosphere in Infinity War. Someone correct me. Does he go straight up following the spaceship, right?
Yeah.
Anyway, you would have to determine what the exact acceleration for Iron Man is. I've said this before in one of my very early videos, where I've less everything going on, that the accelerations that Iron Man puts on himself should kill him unless he has specialized technology. He does. Let's just say that he does. But if we didn't, and we did the same kind of moves that Iron Man pulls off, we would get wrecked. There's a scene in Iron Man 1 where Tony Stark is going at Mach 1. The fighter pilots that are chasing him saying he's going Mach 1, which is 343 meters per second, the speed of sound in air and normal atmospheric temperature and pressure at sea level. Yes. Then you see Tony going at Mach 1, and then almost, it's hard to tell because of the way the movie's edited, but he almost instantaneously arrests himself, kind of counter thrusts by putting up, well, it's counter thrust from his repulsors in his hands, and then he's also getting flaps up on his armor like a plane does when it's landing to slow itself down, and it rapidly decelerates. That kind of deceleration alone probably would make you pass out. If you were going from 343 meters per second to 20 in a few seconds, you're pulling a lot of G's. And that's very dangerous. There's another move, I think in Iron Man 2, where Tony is going very, very fast and then makes basically what looks like a 90-degree turn in his suit with similar change, in direction and velocity. And when you have a rapid change in velocity, that's a high acceleration, and that should wreck him in there, unless Tony came up with some kind of specialized hyper-advanced technology, which you know that he has. So Tony Stark can figure it out, but we cannot do these kinds of maneuvers like that. Fighter pilots can't. You cannot just make a 90-degree turn. You have to slope these things to, they couldn't really make a 90-degree. Anyway, you want to have smoother transitions from fast to faster to slower to done, or else you're dead. What's next?
From Will.
Oh, hello.
Hi, Kyle.
Hey.
How much energy would it require to run the Matrix computer system?
Oh, dang, I calculated this once. What did I say? I forget. It's an old episode where if you take 25,000 BTUs of body heat, British thermal units of body heat, and you multiply that by the population in 1999, you get an energy content value, which I forget what the value is off the top of my head. But I do know that it is much, much, much less than nuclear fusion can produce. Nuclear fusion, the promise of it is that you can get an enormous amount of energy out of a little bit of fuel or what have you, material. It's very energy dense, the process. We use something like coal because it's very energy dense. You can get a lot of joules of energy out of a little lump of coal. Now, let me put it this way. So the Matrix says that they advance to nuclear fusion. If you have nuclear fusion, you do not need humans to power your stuff, and here's why. Let's see if I can, yes, just a water bottle, if you had just a water bottle and it was halfway full, that water bottle, if you just used all the hydrogen in the water and you fused it and you put it through a fusion reactor, let's say, it would release the same amount of energy that a train full of coal pulls around now. A single bottle of water, and I learned this from a very smart person who I will talk about a little bit later, but just a single water bottle can release the same amount of energy that a train's worth of coal could. That's the promise of nuclear fusion. And all that is to say is that if the machines and the artificial intelligence, superintelligence in the Matrix figured out nuclear fusion, they wouldn't need the very basic and inefficient power source such as we. It takes a lot of energy just to grow humans and keep them alive. If you can do fusion, forget all that stuff. You do not need us anymore. What's next?
From Matt XL11.
Oh, hello.
What are the best skills humans have comparing to animals apart from the brain?
Huh. So, I remember the word. Humans are, let's hope I spell it correctly. No, don't take the risk. Humans are altricial, which, I'm pretty sure that's right. Humans are altricial, which means for the first few years of their life, but a period after they're born, they are basically helpless and they are completely dependent on their parents and the mother for protection. And scientists think that this is an evolutionary trade-off for our gigantic and amazing brains. That resources and genetics have been diverted to help our brains grow instead of having us walk straight out of the womb or having us have sharp claws or fast reflexes or a head that isn't squishy enough to poke into right out of the womb. So we think that that was our evolutionary path. We didn't want to start running right out of the womb like a giraffe or a horse does because we have these giant brains that seem to help us pass on our genes better than other animals. So, got selected for it and kept doing it. That's the big thing. That's what humans got going on. I mean, look at this. I mean, I can't even comprehend where I am, and I have a brain. I don't know what that means. But in terms of physical abilities that humans have that are on par with animals, well, we're not the strongest. Pretty sure a gorilla could rip you in half. Not literally. Probably dislocate some stuff. Or rip your... Tangents. A gorilla can beat you in strength. A cheetah or a horse or most running things can beat you in speed. Humans aren't very good on that. What humans are very good at is distance running, and that's what our ancestors and some native peoples and that's what our ancestors and native peoples used to their advantage. If you wanted to hunt down a large prey animal like a woolly mammoth, for example, you would want to. We cannot beat it through speed or strength alone. We have numbers and technology, that's very important. But we can also chase these animals down over miles and miles. Humans are good at long distance running. That's why we're good at marathons, relatively speaking. So we can chase these prey animals over many, many miles until they get tired, and that's when we get them. Humans are good at running a lot. So if anything, I think that is one area that I can think of off the top of my head where humans have a big leg up that has nothing to do with their brains. What's next?
From Data Bing.
Where are you? What?
I'm somewhere.
Yeah,
From
okay.
Data Bing.
Yeah.
Are there any life forms that live in 2 dimensions?
What? I don't know. Every organism. That's a weird question. Every organism that we know of because we are studying it in our own 3 dimensions: forward, back, up, down, side to side. So that's. I don't really know how to interpret your question. To discover an animal that only lived in 2 dimensions, I think we would have to be in 2 dimensions. But, you know, I don't know. It's kind of a weird philosophical thing, like Flatland poses or something. The book Flatland. But for very basic creatures that more or less live on a plane of a surface, like bacteria living on the plane of, a table or something in your house. That's more or less like a 2-dimensional existence. But yeah, I don't know. That's a very hard question. I don't think so. Everything that we know, matter, exists in 3 dimensions. The universe is 3 dimensions as far as we can see right now with our squishy eyes. So I don't know. That's a complicated one. So I'm gonna leave it at that. What's next?
From Matterbeam.
Oh, hey Matterbeam. What up?
I know you've wondered about the energy source for Venom's high-powered stunts. I'm thinking, where does all the heat go? Is Tom Hardy boiling in there?
Well, from just how sweaty Tom Hardy looks in the new movie Venom, I think there is a lot of heat generation. But you're right. And this, I'm going to get to this in the vlog too, but just like the Hulk, Venom has a mass problem. Where is all of the mass coming from? Canonically, Venom can exist on the outside of a person, like an ectoparasite, like we said, but as clothing, and can blend into the surroundings and more or less become invisible. But even if Venom was just the clothes I'm wearing right now, how does it, when it transforms me into Venom, how do I suddenly become, 9 feet tall and big and hulking? Where does the extra mass come from? Is the symbiote very dense when it's closed on me and then it expands and it's not as dense? Is it not adding many kilograms? Is it just kind of spreading out and making itself look bigger, like a kind of goo foam, rather than a solid viscous thing? I don't know. And there's, like you said, MB, there's a lot of things that go along with that, like heat generation. Where does it all go? I can guarantee you these are things that are left out of the discussion when you talk about the script with something like a science advisor, where if someone like me were to bring up, yeah, it's cool that he's goo and all, but don't you think he'd be pretty hot? And then the script writer or the director would say, well, how do we show that? Does it really matter? And you'd be like, well, I mean, he'd be really hot, so maybe? And the director's like, no. Yeah, so there's trade-offs between narrative and scientific accuracy. I think that's one of the big ones for a lot of different things, especially the Hulk. Where does the extra mass come from? But he's big. All I need to know. So that's how it goes sometimes. What's next?
From Phoenix. In the movie Die Hard, John McClane shot at a window and then swung out to break it and to get inside. Would he have to have enough kinetic force to do it, even after shooting the window and weakening the window?
Oh, okay. Okay. You could do the actual math on this. I cannot do the math off the top of my head. Probably. So if you have, John McClane swinging, there's a fire hose. He's on the end as some kind of point mass. See, this is the kind of stuff I like doing with y'all. This reminds me of what Richard Feynman used to do in a class he called Physics X, where he wouldn't tell you where the class was or when it would take place, but students would show up and they could ask him any question, and he would just work through the problem with them on the whiteboard. I love that kind of thing. Anyway, John McClane on the end, swinging through, let's say perfect circular arc. He's a man of, see, this is basically how I do my Because Science episodes anyway. Establish a situation. Perfect arc. Let's assume he is an average mass of person, let's say 62 kilograms, like this. So you have 62 kilograms moving in a trajectory like this. You'd want what the final velocity is at this point, and then you could plug that into an equation for kinetic energy like this. Boop. And then if you divide how much his body deforms before the glass breaks, you can divide force. That's okay. See, this is the problem in doing it in real time. We're just changing kinetic energy. So you divide that by the distance that his body deforms as the glass breaks, and then you can get a force on John McClane's body. Now, the things I don't know is what is the structural integrity of a window after it has been shot. I'm going to have to say that it is less, that it would be much easier to shatter once there's already points of failure cracking inside of the glass. Glass is brittle, that's what happens. What is his ending speed? You'd have to look, velocity rather, you'd have to look at his starting point as he kicks off from the window and comes back on for the force, and then you'd have to say, is that still enough to break a window? I have no idea. I feel like you'd have to look at a lot of technical specifications for glass on skyscrapers. I have a suspicion that the glass on a skyscraper, especially many stories up, as John is in that scene, the glass is a lot thicker than you think up there. And it's a lot windier than you see in the movie as well, which would wreck his parabolic trajectory. Anyway, so the glass is very, very thick. So I don't know if he could make it through. It depends on the thickness. And if he did make it through, something that they never show in movies, which was, I think, the first episode of Mythbusters, is that if you smash yourself through a window, you are going to be horribly sliced up. You're going to have many lacerations. When you crack an amorphous thing like glass, because it's amorphous, the atoms are not in a crystalline structure. So when you break them, they can break off at very, very fine points, like obsidian glass. And you can break off and you can have edges that are just a few atoms thick. And when you have that, you have a very, very thin edge that can slice through you like you're not even there. Because for a small cutting surface, you do not need much force to create a grand amount of pressure enough to push through your sweet, sweet dermis. So, I started you off. You can finish it. What's next?
From Rockin' Randall 12.
Hoo-hoo!
Hey Kyle, is it possible to make a small sun like Doc Ock did in Spider-Man 2?
Funny you should say that. The reason that I was not at this location, I mean, if you can even really say that, the reason that I was not at this location last Friday is because I was at a special location. I forget how I got there, but I was at a special location filming something that is very special that will come out very soon on the Because Science channel that has to do with your question. Kind of. But it deals with the same thing that you're asking. And that's all that I will say. Stay tuned. What's next?
From Hateful Jerk. What problems would arise from becoming fully intangible?
What? Well, sometimes I already feel fully intangible. Does that count? Sorry, I'm just kidding. Angry Jerk? You friend? I don't know. Fully intangible, it depends on what you mean by intangible. Do you mean invisible? Do you mean not able to touch things? Do you mean not interacting with the electromagnetic force as we know it? Are you just passing through? Are you just moving through the center of the Earth like you're in a different phase, like in Star Trek TNG or something like that? Can you not be touched? Do things go through you? Do you not interact with strong nuclear force and stuff like that? I don't know. But I do know that we only exist as we do as creatures on this planet because we are tangible. I mean, just think of how much gravity directs the things that we do, the way that we move, the way that we evolve, the way that our bodies move stuff around just to function, how we live, how we work, everything dictated under the omnipresent pull of gravity. And if you were intangible, all that would go away, right? If you're not interacting with anything. And then life changes dramatically. I don't know, but the question sounds like, hey, don't worry, man. You're not intangible. You can be seen and appreciated. People do it. Trust me. What's next?
From Alan Forsint.
Ooh.
Kyle, how do you think a dragon breathes fire?
Sorry, I was just admiring my spider-frog friendship. I've speculated on how dragons breathe fire before, and for me, it comes down to two different possibilities. One is that the dragons have some kind of sac in their bellies or in their breasts or what have you that are like air sacs. Birds have very different lungs than we do. So let's say they're like chambered. It's not a circular. It doesn't flow in and out like it does in our lungs. Our lungs, air comes in, and then it comes straight back out, and it like circulates with the same air you're breathing in. Birds do not have lungs like that. It just goes down a path and then comes back out. It doesn't circulate with the air you're also exhaling. Anyway, so if dragons had something like that was kind of like bird-like, maybe they had a sac that could store, let's say, the accumulating gases from their stomach, something like methane. And if that organ started accumulating methane, maybe the dragon would also have a way to release said methane into its mouth, let's say through some kind of tube. And if that tube was in the back of the mouth, in the throat, and let's also suggest that like some animals, that dragons, sorry, I'm just thinking, that dragons have to eat minerals and rocks to help them digest because they eat, creatures whole and bones and hooves and hair. So I don't know why I went to Texas. So they also eat rocks and minerals as they go. Now their teeth are coated in minerals. So let's say they release gas from their methane sac, and they click their teeth as it comes out, and there is a spark like you find on the end of the lighter. And if you do that while releasing the methane gas will expand to a point where its stoichiometry is advantageous for combustion, meaning that it mixes with enough oxygen in the air so that it combusts, and because it doesn't just blow up immediately. That's why it doesn't blow up down here. That's why you can't light like gasoline on fire and then the gasoline explodes in the tank. It has to mix with enough air. Anyway, so if that happened, maybe it comes out as flames that way. The other way that I've always speculated was maybe like the bombardier beetle evolved two different chemicals in two different locations in its body that when threatened, they mix those chemicals in a third chamber, and that causes a kind of tiny combustion, and that forces scalding hot acid liquid out of their butts into the faces of their attackers. Let's say that dragons evolved something similar, except those two chemicals combined and combusted into flame, and produced flame when released from their mouths. So let's say they had two of these tubes on either side, and as they spat, and they mix in the air, and as they come out, causes a flame. I think those are called hypergolic. I believe those are called hypergolic chemicals. We use the same kinds of things in some rockets. So what if a dragon had a rocket mouth? Yeah, that sounds like something I'd say. What's next?
From Michael Morin. I told my science teacher gravity is not a force. Am I right or wrong?
Gravity, okay, how complicated do we want to get here? Einstein's big insight, he was a smart boy, was that gravity is more of what the curvature of space-time feels like. So in that sense, it's hard to say that it's like me pushing you and that producing a force. But when we talk about force, we always talk about the force of gravity. The force of gravity on you is your weight. you are being accelerated down. But again, that's not really a force. Your weight is the gravitational pull on you is forcing you into the ground, and the ground provides a reactionary force, and that is your weight, more or less. That's what a scale reads. But two objects in space, based on their radius and their mass, will exert some kind of gravitational force between them. They will have, this is the universal law of gravitation, I believe, from Isaac Newton. And he says that no matter how far two things are apart, depending on their radius and their mass, they will produce a force from those properties alone that will act to pull those objects towards each other gravitationally. So in that sense, gravity is a force pulling things towards each other. There's nothing pushing a planet towards another planet that's apart from the gravitational force pulling them together. So depends on how
Is it possible to still talk to someone like that?
Yeah, it's so cool. Of another one of her Marines from Mars, and like a tin can telephone, the vibrations from her speaking vibrate the air inside her helmet, which vibrate the helmet, which vibrates the other helmet it's in contact with, which vibrates the air inside of that helmet, which transmits to sound in the other helmet. Now, would it be perfectly intelligible? Probably not. Would you have to scream? Probably. Just as good as a tin can telephone is good. So I do think that is an accurate scene. And if nothing else, it is very, very clever, which is why I think you should all watch that show. But you're watching this show right now, and thank you for watching another edition of Because Science Live. Thank you for joining me if you watched the vlog this week and the new episode this week. Next week, we have new vlog, new live stream, new episode. It's going to be a good one. I hope you have a wonderful rest of your weekend. If you want to follow me or Because Science, you can do so at Because Science and at SciFile on Twitter, or you can go to youtube.com/BecauseScience, facebook.com/BecauseScience, or the social handles. And that's all I got. We got a lot of cool stuff coming up for you, so stay tuned. And be nice to each other, because this is all we have.